This is the Art of Network Engineering podcast. In this podcast, we'll explore tools, technologies, and talented people. We aim to bring you information that will expand your skill sets and toolbox and share the stories of fellow network engineers.
Oh, Detective, I'm glad you're here.
Sure thing, Chief. What do you got?
Well, this is something we've never seen before. We've definitely come across nests of cable before, but nothing quite like this. These cables, they have no copper in them. I'm talking 0 pairs here. They appear to operate with some sort of laser shot through them or something, but we're not really sure.
A laser, huh?
That's what I said. Have you ever seen anything like this?
Indeed I have. And Chief, as far as this investigation goes, you could say that we just shined a light on it.
Welcome to the Art of Network Engineering. I am Lexi, aka Track It Pacer, and I'm joined by Mr. Tim Bertino. How are you doing, Tim?
I'm doing well, Lexi. What's up with you?
Not a whole lot. What did I say last time we recorded this? This may or may not be our third or fourth time trying to record this specific episode, so, you know.
But we believe so much in the content and what's going to be shared here that we just keep trying.
We desperately want this the content of this episode to be released successfully. So I had a decent day today. Did some troubleshooting in the lab. Can't talk much about it as per usual, but it was good and fun, and I learned a lot. Something rocket adjacent, I guess. What have you been up to?
Any day in the lab is a good day.
Oh yeah, for sure. Lots of hands-on work. What about you, Tim? How was your day? What you been up to?
Pretty good. Delving more into many things software defined. Specifically on the Cisco side with software defined access, really getting into that software defined campus kind of thing with Lisp and VXLAN and all that fun stuff. It's been really good. It's definitely a different way to manage networks than a lot of us are used to. And as we all know, change can be hard
for sure.
for some more than others. So it's been fun.
Lisp is fascinating. I haven't gotten around to studying VXLAN in much detail yet, but Lisp I had to learn for, I think, the Encore test maybe. And that was very interesting. I hadn't encountered anything quite like it before. So
yeah,
cool.
And I'm not trying to be an expert by any means. I'm just trying to know enough about those to be able to somewhat troubleshoot if I have to, because that's the whole thing with Cisco's SD Access is they use DNA Center to really abstract all that away. So you don't actually do any of the configuration of Lisp and VXLAN. It's all done for you. But just me being me, I want to make sure that if I need to figure out why something isn't working, I can at least point myself in the right direction quickly.
Good old CLI. Cool.
Yeah, there you go.
Awesome, Tim. Well, today we are joined by a special guest. We have Iain Geddes here today with us. How are you doing, Iain?
I'm good, thank you.
Iain, you're a technical leader at IBM. Is that right? He nods his head. Yeah, we'll go with that. Okay.
that's committal, right?
Iain's a network engineer at IBM on their hybrid cloud platform, and he happens to be a former coworker of mine. So I'm very excited to have Iain on today. And our subject is Optical Networking 101. So we're trying to cover the basics of optical networking. Not super in depth, but we want to kind of start with you, Iain, on like what is optical networking? What are we talking about when we say that? Right.
Well, it's kind of like asking what's networking, right? It's a lot of things to a lot of people, and it just depends on where you want to start out, right? So it's everything from, a fiber optic patch cable inside the data center, right the way through, connecting countries together across submarine systems and all of that excitement. So I mean, obviously the intent here really, we're starting with the basics. So the focus is really just the data center. We don't want to go too wild, obviously, because
we don't want to go
putting people
submarine.
to sleep is not the plan.
Is that true?
It's interesting, right? When you start peeling back the layers of what it actually means to have a signal being able to transmit across an ocean, it becomes insane, because obviously you don't have the ability to plug in anything in between. You've got 6, 7, 8,000 miles between where you put the signal in and the very next place it hits Earth. Yeah,
that's wild to me that we can do that. I know it's been a thing for decades now, but it is wild how far we. And
it's becoming more and more insane. I mean, that's the reality. It's the amount of data you can get into these systems is just ridiculous. It's unbelievable, even the changes over the last few years. But again, that's not now. Right.
Yeah,
There's a whole new other world of pain before you get to that.
Yeah, let's start with the very beginning, at the very, very basic level. I think we know that optical networking, there we go, I got it, has to do with fiber optic cables. Is that right?
Yeah. Okay. Really exciting stuff.
Yeah, tell us about it.
Tell you about it. It's exciting. I mean, just starting at the very beginning, the fiber, the cable, here's one I made earlier. Nothing amazing to it, right? It's a piece of glass basically that's been just stretched so it's really, really thin. And it's a waveguide, right? The whole point is to be able to guide the light in the direction that you want it to head into. Yeah, that's all it's there for. The same as a radio antenna is used to project a signal in the direction that you want it to, and a receiver on the other end is also directional to pull it out. Yeah, the fiber obviously is physical end to end, but it's, I mean, that's the excitement of it. So kind of, just starting at the very beginning. One of the reasons that we're doing this was just because the CCNA covers kind of what is fiber, right? It comes up a little bit in Encore, but the reality is that for most people, it's just a line on a piece of paper, right? We don't think about it too much. We connect things together with a cable somehow, and whether it's fiber or copper or whatever, it doesn't really matter all that much. Now, obviously, when you start having to do it, it kind of seems a bit magical in a way, but the reality is it is just kind of either another cable or it's something that's really fragile and scary because it's glass. Yeah, so depending on kind of your introduction to it, shapes in kind of a big way how you perceive it, right? And the reality is it's neither. We'll get to that in a bit, but it isn't just another cable. There are things that you can't do with a fiber that you can do with a copper cable, right? And similarly, it's not this fragile thing. It really is quite a robust cable, but you've got to be a little bit careful. Yeah, at the end of the day, it is glass, right? But it's not like a glass. It's not something that if you drop it, it's going to shatter into 1,000 pieces.
I feel like that's one maybe myth or difference that some people think about fiber optic cable.
There's a bunch of kind of strange ideas that grow up around it, right? Because again, it depends on your exposure, but because it's something that people generally don't think about, because CCNA doesn't really touch it. Yeah, they go into great detail about the cables and the pinouts of the copper cables. And an awful lot of people get to create their own Ethernet cables, right? Whether, by accident, they just find themselves having to, or, it's something that's done in a classroom once and they never want to do it again, or because they're trying to create the world's most perfect patch panel. Whatever somewhere in between, probably for most people, that there's a reason that they're out on site at 3:00 in the morning and there just isn't that perfect length of cable. So they've got to, kind of trial by fire, if nothing else, watch a YouTube video. I can do that. I've got the tools. I can squeeze a crimping tool, whatever it might be. You can do that with a copper cable, right? You can't do that with fiber. It requires expensive equipment to splice, is what it's called in a fiber world, because you're literally fusing two pieces of glass together, and it's so small that you can't do it by eyesight, right? It's a machine. You stick it inside a machine, press a button, it does the lining up, and magically tells you it's done. So you don't really know that much more, even when you're doing it for yourself, than you do at the outset. But yeah, so that's kind of the excitement. I'm just trying to think. It's the reason for fiber. There's a bunch of them. The main reasons really are things like it'll go further, right? With copper cables, obviously you've got limitations within the data center of how far you can actually get to. Somewhere about 300 meters is kind of the maximum that you're going to get with a copper cable. And again, depending on what kind of speeds, because the way that the copper cable works is that you're transmitting on multiple pairs at the same time, and between those pairs you get noise injected, right? So the greater the distance, the more the impact of that noise. Crosstalk is what it's called, and any external noise as well gets picked up by the cable. So the faster you're transmitting, the more noise that's been getting generated, and so the shorter distances you can reach. Yeah, so you buy more expensive cable, so you can go further with higher speeds, because there's more shielding, the way that it's twisted together, all that exciting stuff. But you're still limited, really, to modern cables at 10 gig plus, or really kind of 100, 150 meters is kind of pushing the edge. But yeah, with fiber, 300 meters is kind of the starting point, right? We can do 300 meters with our eyes closed and a cheap cable. You can push a signal, just with standard optics that you just buy and insert into the router. You can push a signal for 60 kilometers.
Let's talk more about the differences between, I guess, what maybe coming out of CCNA or more beginner courses we're used to with like copper, Ethernet, cables versus fiber optics, right? Can we touch more on that? So you mentioned, fiber can send the signal further than copper. What else? What other like basic differences are there between the two types of media?
The main difference really is that the distance, right? We've got the other thing is, because it is just a small thing of glass, the bulk of the cable is a lot smaller, so you can easily kind of carry, and service providers they'll carry lots of fiber in one tube. So what looks like one cable could actually have like 70 pairs of cables in it. And we have that inside the data centers as well. It's a nice, easy way of connecting patch panels together, for example. Right? You just run one physical cable that's not that much bigger than an Ethernet cable. And in there, you could have, 20, 30 fibers all together, and it all just runs together. It's all nice and simple. And we can break it out with these weird connectors and all the rest of it. And it plugs in and it all just works, right? It's magical. I don't like using those terms, but that's how it's sold. It's not something we can do.
Demystify for us. So how does it work?
I've got to start somewhere. I've got to build it up, right?
Yeah.
So
can we, since we're talking similarities and differences, let's talk about some of maybe the, for lack of a better term, bad things that copper is susceptible to. Do the same things apply to fiber? Like, I know one of the things, I was always told coming up was with copper cable, you want to keep your copper cable away from the power cables because there could be that interference there. What do we have similar things on the optical side with fiber?
So no, because it's light, it's not susceptible to any electrical noise, right? So with the power cables, for example, it's kind of a bit of a misnomer. Excuse me, kind of a bit of a misnomer because the way that the cable's created, the way that the different copper wires inside the cable are run, they wrap around each other, right? And so the whole point of them wrapping around is that when you have something like a power supply next to it, AC cables or whatever it might be, the signal that's being emitted from those, that's kind of influencing our Ethernet cable, is impacting kind of both strands of that together, and it kind of cancels itself out, right? So there is shielding in there. There is, the susceptibility to electrical noise is minimized, and that's why the more expensive cables like the Cat 6 versus Cat 5. There's more wrapping, the twists are more dense. And so as a result, you don't have that same problem with noise because it cancels out. But again, the fiber doesn't have any of that problem. So when you're running somewhere else, somewhere like where there's lots of electrical noise, like generators or motors or a lift or something like that. If you're running a cable through a building, you're subject to a lot more noise in there. Even things like overhead lights can give quite a lot of noise, and the cables will pick it up. There's no question, right? It'll cancel, but that's what limits the distance you can take your signal. With optical, you don't have that at all.
And why is that?
It turns out because it's light. So the electrical signals don't really have any impact. Should I try again? They don't have any impact because there's no copper in this cable, right? There's nothing to pick up that electrical emission from the power source.
So we've danced around this.
Yeah, so nothing to interfere.
We've danced around this a little bit, but I don't think we've actually explicitly said it. How is data being carried over optical fiber versus, like, we know that, copper cable, it's electrical signals, but.
Yeah. So at its very simplest, if you just think about sticking a light bulb on the end of that thing that's generating that electrical signal, right? So you've got a flashlight, right? And as it flips on and off, magic, right? There's your optical communication.
So it's light instead of electricity.
It's light, yeah, absolutely.
So there's light running over glass is an optical fiber, basically, right?
Yeah,
okay.
That's in its simplest form, right? And as a child or whatever, we would have been playing with flashlights and communicating. I'm going to flash this twice and it means something, 3 times and it means something else. Whatever it might be. Morse code, right, would be another example of where you use like a flashlight, dot, 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 dash, dash, dash. The length of the pulses is sending the message, right? But it doesn't necessarily have to represent anything. Yeah, it's just a sequence that you can recognize to mean that that's what it means, okay? With, when we're talking about Ethernet or something like that, it's not about dots and dashes. It literally is about the light being on or off. And so if you think about just kind of dividing up, counting basically. So if you count seconds, and so you're looking at whether the light is on at second 1, second 2, is it on or off, right? Second 3, on or off, 4, on or off. So you're counting the spaces. So maybe to try and help this, I have got some slides, but it's not, the intent here is obviously not to make this a death by PowerPoint. It's just because some of these things are kind of hard to explain. And now I've got my image inside an image. So this is, a clue to who I am. I'm clueless.
Love it.
There's the light, right? So it's this idea, right? We divide time up, and at certain moments in time, see, I should not be allowed to drive PowerPoint. So at certain moments of time, the light is either going to be on or off, right? There's nothing more complex than that. And so, you're just going to read it just the same as you do bits on a wire.
So on, I take
right?
it
So
is a
1, 1, 0, 1,
and off
0.
is a 0.
Yeah.
Okay.
Absolutely. Now, obviously, when you think about what's actually involved in getting this to work, you start realizing very quickly that this thing's enormous, incredibly fast, right? Even, a simple 100 megabit per second interface, if you're detecting 100 million bit positions every second, that's very short periods of time. Yeah, but it's exactly the same as with a copper interface. Yeah, again, like I said, you're just reading ones and zeros, nothing more exciting, nothing more than that. So the point of these two arrows that are on here, so in the sixth position and the whatever it is, ninth, is 10th, it is just the encoding techniques that's used. There's not much point worrying about it. Again, it's exactly the same as with Ethernet, that those bits are used as a checksum for the pieces that go either side. So we know, sorry, they're not a checksum at all. I'll get it right one day. They're used to make sure that we're synchronized, right? We're reading these things so fast. We've got to have some things that we know we're going to have a state change from a 0 to a 1 or 1 to 0. And that's what they are, because otherwise, if everything's on all the time, if you just try counting, if you work with a clock, right, and you're counting seconds, you'll be right for the first 10, 15, 20 seconds, maybe. But over time, it's going to drift. And so at some point, you're going to be off by a count or two. And if you're off by 1 or 2 here, then your message is now not coming through anymore, right? That where you're supposed to be reading this one, you're reading this one. And so, if we're off by 1, it becomes that, all data is gone.
So you're talking
So
about
that's what those
clocking
synchronization
information
bits.
that's sent with Ethernet, right? So we're running.
It's with Ethernet as well, right? Okay. It was just, while I was looking at this, it was kind of cool because I'd never thought about it, right? Literally, the idea of trying to read the state of a light or even a bit at that frequency is something we can't even begin to understand, right? And obviously, you take it up from 100 megabit. No one uses 100 megabits anymore. 10 gigabits, or 10. Well, you want a rocket. In fairness, you don't need anything. You're not downloading cat videos, right?
You don't know what I'm doing on a rocket.
I don't know what you're doing, but I'm saying that in general, that's probably not a priority for the space station. For the rocket.
Right now, maybe. Okay, so
they're not going to be looking at cat videos while they're flying.
Says you.
Hopefully.
No. Okay, so Ethernet can run over fiber just as well as it can run over copper cable, right?
It's Ethernet, right? The difference, like I said, is little more than you've got a light bulb attached to the end.
I think a lot of like people
newer
newer to networking might, because I know this because I fell into the trap when I was learning early on.
Oh yeah.
We think of the actual copper cable, we call it an Ethernet cable, right? And so we start to think of that cable as like Ethernet is the cable, right? It's the physical medium rather than a protocol that just runs on that physical medium. And so sometimes I think when your mind expands a bit into, okay, there's actually like optical fiber that we use and Ethernet runs over it, you kind of get jolted out of that, like, oh, wait, Ethernet is a protocol, right?
Yeah.
It's not, fiber optics are not like Ethernet cable as we know them. So it gets a little confusing, but it's good to know, like optical fiber carries the Ethernet protocol. You can run it over, that medium just as well as copper.
Yeah, absolutely.
Yeah, I'm so glad you highlighted that, because I think it's easy to fall in that trap where copper and Ethernet are synonymous. And again, it's Ethernet is the protocol that can run over copper or fiber mediums. Yeah, really glad you called that out.
So yeah, I mean, one of the most basic things to, and it kind of blows your mind, because again, you don't necessarily think about it, is just that the idea that light isn't just light, right? So there's a color to it, right? So here's it's a fairly common science experiment that's done in school to excite young kids, but we see it in rainbows, we see it in any time water's passing through a raindrop, right? There's nothing amazing about it. We have this white light, and it splits out. I'm trying to think of the technical term now.
Is it what we use?
I'm sorry.
Is it refraction?
It's refraction that's causing the colors to split out. Absolutely. And what this means is that we've actually got multiple colors inside that white light. Okay. This is something we'll come back to later on, but it's the idea that we can have something that's sending light as this red. Okay, and we can have something that's sending light as this green or this purple. Yeah, whatever it might be. And we can do it all at once if we want to, right? We can send those, pass it into kind of a reverse prism and spit the white light out, and at the other end it can break the signal back out again. Yeah, that diffraction we'll spread it out in exactly the same way at the other side, and we'll be able to pick up on that. The reason for mentioning this, we'll come to in a bit, but it's kind of an important concept to think about, that when we're talking about light, we're actually talking about numbers. So here's kind of an example. This is, I'm showing kind of a picture of the electromagnetic spectrum and where visible light fits in it, right? So there's a very small band in the middle. For anyone who's just listening to this, don't worry about it. There's nothing exciting. Again, it's just showing where the rainbow fits inside all wavelengths, all of the electromagnetic spectrum, right? Which goes all the way through from radio waves to X-rays and gamma rays. The stuff we're working with is just outside the visible light spectrum, right? We kind of take from this point just to the edge of visible light. Okay, so while we're showing the idea that you've got all of the colors of the rainbow in that visible light space, you can see that they've got numbers associated with them, right? So this shade of red is 700 nanometers. Yeah, this shade of red here is 720. Yeah, down here we're looking at this blue, that's 420, 40, 60, 480-ish. Yeah, it doesn't matter. The stuff we're talking about is slightly further up in the spectrum, but this is a good kind of reference, a good, easy way to think about things, right? We're going to give the light that we're using a number so that it's got its own unique space when we join it all up together, or just send it in as light to pass across the fiber. Okay, does that confuse anything? I know it's kind of a bit of a weird thought.
No, that's pretty
but you'll
clear.
see where it comes in a bit.
It's really interesting.
Okay,
so
cool.
we're not talking about the, I guess, refraction of light. It's all different colors inside of our fiber cable. It's the opposite, but these colors come in to play at some point still. I don't want to get
the
too
joining
ahead.
of the. Yeah, no, it's all good, right? It's it's probably a few more.
Don't let me derail.
Where it actually starts talking. But no. Again, the idea is that we have all of these colors available to us, right? When we're seeing it from a rainbow, obviously the sun is a random noise generator, right? So there's not actually any signal inside there for us to make sense of. Yeah, we can't take that red color at 700 and try and make sense of is that a 1 or a 0? Is it on or off at this particular moment in time? Because it's meaningless. But we can do something like that, right? We can have a laser that's transmitting, kind of jumping ahead a little bit, but 850 nanometers is a multimode laser, right? So that's literally just falls outside of that visible light spectrum. And if you look kind of carefully in a dark data center on a dark night when, the moon's hidden by clouds and all the rest of it, you can actually see that red spot. Yeah, it's not that it's invisible. It's not dangerous. It's not going to kill you or anything like that. You can see that red dot. That's the laser that's sending the data. Now, obviously, you can't see it flash. That would be really cool if you had eyes that were able to be that sensitive. But it's there, right? As we move up in the spectrum, as we come into, the 1300s and the 1500s, those are the single mode wavelengths, and they're used for kind of local connections and distant. Again, we'll come to that in a second, but those ones you can't see, right? The 850, the multimode, is right on the edge of our visible spectrum. So that's why we can get to see it there. Okay? So just very quickly, small detour. I know this is about light, but I wanted to introduce kind of the main terms that affect the ability to send a signal, right? And these are in terms that you already know. These are things you're already familiar with, right? So the main thing is about attenuation. It's about the amount of loss that's in the system, right? In the cable, in the connectors, in all of the pieces that come together. The difference between what you send and what you receive is the attenuation. It's the loss. Okay, and literally, I mean, this is a picture of a pair of earplugs. Those earplugs are there to attenuate sound. Yeah, so they've got like a 20 dB, 20 decibel reduction in the sound that's reaching your ears versus what's there without them. Yeah, that's the loss that's been introduced. Okay, and it's just about a noisy source being quieter when it's at the far end, right? If you're in a room, you're stood near to someone and they're talking to you and you walk away, then obviously their voice is becoming, or the signal of their voice is becoming attenuated by the distance. Yeah, it's just getting quieter.
Okay,
and so you get to a point where you can't hear it anymore.
The same thing happens with
It's exactly
fiber.
the same in optical. Okay. Yeah, absolutely. And distance is a part of that as well.
Okay, I kind of wanted to dig into that. I think a lot of us, back to how we talked about, CCNA and in earlier studies, we hear a lot about copper and how attenuation and loss with the electrical signal.
Yeah.
How do we have loss with light essentially in a vacuum?
Well, it's not in a vacuum, right? It's in a piece of glass, and that glass has impurities in there. So, it's even when it's as perfect as it's possible to be, you've got molecules in there that are going to cause some reflection. Something is in the path that's going to cause a little bit of light to reflect, to go in a different direction. And we're going to talk in a second about how it gets along with fiber. But realistically, it is just that. It is, it's passing through there, and there's a certain kind of, there's amount that's getting lost every meter, every kilometer, right? And it's measurable. It's something that you plan for. It's part of the design, right? 0.3 dB per kilometer or something like that. It's a small, tiny amount, but there is some. And it depends on on the fiber. It depends on a lot of things. It depends on how you're treating it. If you've been nice to it and treated it nicely and taken it out for a meal and stuff, it'll probably be nicer to you and give you less hassle. If you mistreated it, then obviously it's going to be a world of pain for you.
What are we talking about again?
Yeah, it's about light, obviously, Lexi. What do you think we're talking about? You've got to wine and dine these things. That's why it's unpredictable.
That's what I was doing wrong the whole time. All right.
Absolutely. but no, I mean, obviously I jest. But when we're installing these things, if we're not paying attention to what we're doing, we can increase the attenuation because light travels in straight lines, right? That's a fact, right? You turn on a flashlight, it goes out and projects onto something in the distance. Light travels in straight lines. If there's anything in between, so other connectors, for example, even right at the very beginning, right, you're plugging a fiber onto the end of the laser, there's some loss there because it's not a perfect connection. We try, but it's not perfect. So there's some loss with every connector. There's some loss with distance because of the impurities in the glass. There's some loss because it's not been installed great. Yeah, and
makes sense.
It's a good start. Okay. So the other term is kind of the result of that, right? Receiver sensitivity. It's about the measurement. So this is something that gets spec'd out on the transceiver, right? On the electrical optical conversion thing that you plug into the router. This is the thing that literally part of the spec, it says, I've got a sensitivity level of however many dB, right? I can transmit at this, I can receive down to this level. And it's just literally the point at which you can't hear anything anymore. Yeah, so if I start talking quieter, then obviously, it gets harder to hear me. And if I talk quieter again, it becomes harder and harder, right? If I start whispering, I'm going to get to a point where the message I'm sending just isn't getting through. And it's the same thing here, right? If you're in an environment where it's kind of loud and you plug in earplugs, then you've attenuated the sound being received by your brain. If I'm talking, you might hear it as a whisper. If I'm whispering, you're not going to have the first idea what I'm talking about. Yeah, what that message is about. Okay. And I think, actually, I just got ahead of myself 1 second. This is the same example, right? It's just kind of a worked example using sound where we say this, anything less than 30 dB using is a sound meter, I don't know, an audiometer. Anything, these levels, they don't mean anything, right? Don't try and read anything in. It's just trying to make optical the same kind of idea as something that's already very familiar. So there's kind of this, that a whisper measures at 30 decibels on a sound meter. A conversation is about twice the volume, right? It's 30 to 60 dB. Yeah, I'm going to shut up.
No, that's great.
A conversation at 60 dB, it is something you can pick up on. So if we go back to those earplugs that had a rating of 32 dB, it's just maths. So it takes that 60 dB down to just about the same level as a whisper. It would take a whisper down to nothing. Yeah, so you kill the signal, essentially, by having too much attenuation and not enough sensitivity.
So for podcast listeners, we're looking at a picture of like a sort of a scale of, common things that cause noise. And we see like at the very top, the loudest is 80 dB, a kitchen blender. And at the bottom, we have 10 dB, an empty room with no people or running appliances in it, right? So it's this interesting scale that kind of helps you understand, I guess, like this is audio levels, but we're talking in terms of what, like light attenuation, right?
Yeah, we're talking about, we're actually going to be talking about light, but that's measured in decibels as well, right? So it's the same idea. It's all analog. And so, as things double in, I'm not going to go there. Sorry, shut up, Ian. It's not, the numbers don't mean anything, right? It's more just that reflection that if we introduce a loss of 32 decibels from the earplugs, then it's going to make a dishwasher quiet. Yeah. I mean, that's not rocket science to any of us, right? If we've got something in our ears, we can't hear as well. And obviously there's a point where you can hear the whisper, and there's a point where you can hear the noise of the whisper, but not actually what the words are, right? Your brain can't reconstruct enough of that signal to be able to make out what that actual conversation was, that message was. And that's the point of I don't know. Receiver sensitivity.
Okay.
Yeah, it's the point where you can't understand anything anymore. Okay. By the same token, it works the other way as well, right? If I start screaming into the microphone, it's going to clip. And so lots of the message isn't going to get processed anymore because it just can't, your brain can't handle it, right? If someone screams in your ear, you know that they're not happy, but you're not necessarily picking up on the entire message, okay? So that's about the extent of this exciting detour. It was just to try and bring it back to something that we're familiar with, right? That's the idea. Stunned by the application of science there, I can tell.
Yeah. It's very interesting.
I'll say if you do want to learn more about the math behind it, it's pretty heavy. I'm sure Lexi, you remember in the prepping for the Enterprise Core exam, is the +3, -3, all that, +10.
You see, it's not.
It took me a while. It took me a while to wrap my head around that. +3 is double, but +10 is
10 times.
And then you start talking logarithmic scale.
It's the logarithmic scale.
That's exactly it.
There's a reason because I didn't take calculus. Yeah. No.
Yeah, and it's all relative as well, right? That's the where things come in. This is where the dBm comes in, because it's got a reference point of 1 milliwatt, right? So that everything then scales from there. The loss, the attenuation, is measured in decibels, right? So it's a ratio. It's the difference of input versus output. So yeah, it all gets messy.
That's enough of that. But we're talking basics.
But that's about the extent of the maths. We're not going to worry about it. There's a lot of physics. There's a lot of other stuff. But for day-to-day use of this, you don't need any of it, right? I was working on these systems for 20-some years, and the amount of times that you actually use that information is so rare in operations.
Good to know. Thanks, Encore.
Right? Because the system's been designed to work in that space. Now, for Encore, obviously, it makes a difference, right? If you're thinking about 3 dB being double, it also means it's half, right? So if you're receiving 3 dB less light than you...
I'm going to cut it off. No math.
Okay, shut up.
No math.
No math. We're done.
Only
We're done.
A space where I get to make a snarky comment about Encore, and we have to move on. That's it.
We'll move on. It's all good.
We're talking about fiber today.
You're in control. Yeah, absolutely.
Hey everybody, Lexi here. Our friends over at NetAlly just announced the next generation Etherscope NXG, the first and only analyzer of its kind that fully supports Wi-Fi 6 and 6E. This powerful all-in-one instrument can help you quickly test, verify, and troubleshoot technology upgrades and base T, PoE, 10 gig, and Wi-Fi 6 and 6E networks. So check it out. Go to netally.com/Etherscope to request a virtual demo.
So
we left off at attenuation,
so
right? And we're talking about receiver sensitivity.
Yeah, so now we're back on light again. And this is, again, it's another kind of stupid graph. Its only purpose in life, really, is just to show kind of why the numbers that were picked, right? So this is the loss of an optical fiber. And what happens is there's a certain range that we can actually send light in. So remember that every color of the rainbow had a certain number associated with it. Visible light was down here, right? It's below 0.7 micrometers as they've got it here, okay? And the attenuation, the loss of the cable, is affected by the wavelength, right? I'll try again. The wavelength is impacted. I've even got this backwards. I'm sorry. The light will travel down a fiber until a certain point when suddenly it won't pass light anymore, right? So once the wavelength gets to a certain level, the loss just shoots back up again. So between kind of outside of this range, of 0.7 micrometers, so 700, can't even do the maths now, but it doesn't matter. We're not going to worry about these things. 700 nanometers to 1.7 nanometers, you can see there's a curve, right? And the idea is that we want to pick places where the loss is the minimum for, to be able to send a signal, right? And so what happens, these things in the middle, there's these things called OH absorption peak, which is water, right? It's basically water molecules in the fiber will absorb those wavelengths, particularly. I don't know why. I don't care, right? That's somebody else's problem. That's why they figured these things out, okay? And so the idea is that the closer that we've got into visible light, the cheaper the optic is, okay? So when you look at here, kind of where's the cheapest place that it makes sense to pick? Oh, just here before that peak. Yeah, so if we follow that down, that's say 150 nanometers. Yeah, and then as we go along, we've got another peak. Oh, it's getting kind of low here. So let's have another one. So, 1310 nanometers is the next one. Like I said, this is multimode. We'll come back to multimode and single mode in a second. But multimode, the first single mode, which will get us, 10 kilometers. And then if we want to go any further, we want to get into this space up here, right? So somewhere in this nice flat part of the spectrum, somewhere around about 1500 to 1600 nanometers, that's used a lot for long haul transmission. And then after that, things kind of go a bit wild, and the attenuation shoots up again. So that's the entire spectrum that we've got to work with, the range of colors between those places. Okay, so yeah, again, 850 nanometers was chosen because it's the closest place that we've got to visible light. It's great for low cost. It used to just be an LED that flashed on and off. Now it's pretty much a laser, but that's because of speed. Not so much distances, but because it's got to react so fast. 1310, slightly more expensive than that, but we can go further. The loss is 25% less. We're down at somewhere about 0.7 dB per kilometer or something like that versus just around 2-ish. Yeah, and then 1550 again, most expensive. The lasers are really kind of precision at this point, but less loss again, so it can go further. We can naturally transmit more power into the fiber. Yeah, there's some physics stuff here as well. Doesn't make any difference to us. Okay, anyone who cares about that stuff can put themselves to sleep. Okay, that sounded bad. I probably shouldn't have used those terms.
We clearly haven't.
Now I think about it, but I'm
podcast. Good. We say worse all the time.
Yeah, but fair enough. So yeah, when we're talking about how light goes along a fiber, we said light travels in straight lines, right? So literally, if we look at like I've got a picture here of, this thing we're going to call a fiber and a light source. From that light source, light's coming off in multiple directions, right? It's not a laser, obviously. It's just a light bulb. So light's coming off in all directions from there. And it's coming into the core of the fiber, right? The fiber has two pieces to it. It has the cladding and it has the core. The core is that ultra fine piece of glass that we're actually using to send it in. The cladding is kind of a plastic wrapping for it, if you like. And its purpose in life is again, it's a physics thing. It's got if you've ever, again, another kind of science thing that was done as a kid is to take a pencil and stick it into a glass of water, and you can see that the pencil actually bends as it hits the water, right? It's I can't even remember what the term for that is either now.
I thought that was refraction.
It's because the refractive index. Yeah, it's refraction, absolutely. The refractive index of air is less than water, and so as a result, you'll see bending. With the fiber, the core has a higher refractive index than the cladding, and so light bends back into it. So literally you have this case where any light that was coming in perfectly straight will kind of travel perfectly straight in a perfectly straight fiber. Yeah. Any light that's coming in at a slight angle, it's going to be like drunks, wandering down a corridor, right? They're going to bounce off the walls as they make their way along the corridor. And that's kind of an easy analogy to make, except...
No, it's true. I'm speaking from experience.
Cool. There you go then. So now you know all there is to know about propagation of light in a fiber.
Now, is that what we want?
That's all it is, right?
Do we want, because you have a picture here of a light bulb sending light through that fiber, and there's a few different colors, and only one of them is going straight.
Yeah, the colors.
The others are bouncing.
The colors here.
Yeah, it looks messy.
Sorry. The colors here I'm just using to identify the path that it's taking, right? Because the one piece of maths that actually matters is that the angle that it kind of hits that outside edge is going to match the angle that it reflects at.
Now, do we want that?
Yeah, just like throwing a ball against a wall.
What does this mean for us with data, right? Like, do we want, are we using all of these colors? Do we want it to be refracting, or are we just using the one part of the light, the one color that's going straight through? What does data?
Yeah, you're using everything that gets into that fiber.
Okay, so all of these. Okay.
So this is where we get the concept of what's called multimode and single mode. Multimode means, hey, there's multiple ways of getting across this, right? There's multiple paths available to us to bounce off at these angles and get down the fiber. And you can see the problem, right? That if you're making a decision whether a light is on or off at 10 billion times a second, then having different paths for the light to be able to travel is actually going to cause us a problem over time, right? Because, yeah, it's passing at the speed of light, give or take, because it's bouncing off the sides. Yeah, but this corridor really is kind of narrow, so it's not that big a deal. But again, you're talking about 10 billion measurements every second. Yeah, so if you've got multiple paths for that light to travel, then what's going to happen is you're going to end up with light on the fast path in the middle getting to the end faster than light that's on the worst one. So the blue line in the middle, for example, bounces 2.5 times, or 2.5 times, whereas the green one bounces 2 and the red one bounces kind of 1 full cycle. So we've got all these different ways the light's getting there, and obviously that light is representing that on and off state. Yeah, so if you've got enough distance between you and the bulb for these signals to get messed up, then things are going to go bad. Yeah, it's not.
Yeah, that makes sense.
It's not that we're looking for a perfect on or off. We're looking for an on-ish and an off-ish. Yeah, there's a certain threshold that we'll accept as this is on, because perfection is impossible. But yeah, having multiple ways means that you're going to get to a point where somewhere on that fiber, you'll be getting light from the pulse before. Yeah, it just took that long to get there. Okay. So that's why multimode fiber is limited to about 300 meters. Yeah, we can't use more than that in a data center. And the reason is because it has multiple ways. And so to avoid any problems with a signal getting messed up, we just say, okay, then 300 meters, that's fine. That gives us the speed of light to travel. It doesn't actually travel at the speed of light, surprisingly, but it's traveling fast enough.
Multimode, basically, the longer the longer your cable is, the
harder it's going to be to distinguish.
The more your light's going to get mixed up and bounce around too much for data to be readable. Okay.
Yeah, and that's.
So I don't want to get too far ahead because I'm guessing you're getting to this next. But if that's the case, and maybe I'm misinterpreting, but it seems a little less efficient, then why do we still have both multi-mode and single mode applications within environments?
Cost.
Is it a cost
Absolutely.
thing? Okay.
Yeah, that's the bottom line. Although even that's kind of changing, right? But yeah, for the idea really in a lot of data centers is, or local use, right? If you're connecting one rack to another, you don't have distance, right? It barely even registers that there's a connection going at 200,000 kilometers a second or whatever it is. There's my indication of how much I care about the speed of light as well. So, this is my subject, and the numbers, whatever, it's close enough. Two-thirds of the speed of light is what it's passing through at. And that's plenty fast, right? We're not worried about it particularly. But to get from one to the other, it's a fairly cheap fiber. It's a fairly cheap optic. It doesn't need to be precise. It's good enough. When we're trying to go further, so if you're in a data center or in somewhere like an Equinix facility where you've got some space in a rack and you're connecting to somebody else, typically you're going to use single mode at that point because it's going to go further than just your room. Yeah, that 300 meters is going to get broken fairly easily. And so as a result, we go to single mode. So when I say that it's generally multimode, that's true, right? It depends on how much you use it, right? Because there's a point where the calculation becomes something else, right? It becomes a question of what does sparing look like? If I've got to spare a whole bunch of multimode and a whole bunch of single mode, then maybe it's worth the extra cost just to save that problem. Yeah, to equip everything as single mode and we're done. It's all good.
Okay.
Yeah, we're not going to go with expensive optics even there. It's enough to close 2 kilometers or something. That's perfect for inside a building. What kind of building are you going more than that? When we get beyond that, obviously things get very different. But again, that's more something for another day. Okay.
So we have the greater capabilities. We have the capabilities of greater distance with single mode. Does that in turn mean we have capabilities of greater bandwidth with single mode than multi mode?
Yes is the answer. But it's more because of the precision of the optics, right? As the speeds increase, there's a whole bunch of compromises that happen. So probably touch on this again later, but it doesn't matter, right? Once you get to about 10 gigabits, we know how to do 10 gigabits. It's been around for a long time. It's fairly easy to achieve. Once you get beyond that, it starts becoming quite expensive because the little bits of copper on the transceiver, on the optic itself, they start acting as antennas because the frequency is increasing so much. And so you get a lot of noise start being created and your signal gets all messed up. So you have to redesign how things look. And so what they actually do for multimode, when we go into 40 gig, for example, is instead of having a 40 gig optic, we have 4 10 gig optics to keep things cheap. Yeah, and then you need 4 sets of fibers, which, it's kind of messy, so it uses a different connector. But
I've never understood why that was the case. I've heard that once you get there, you just have 4 breakout cables, but I never really understood why.
It's just, again, it's cost. It really is. Trying to push the higher the frequency that you're transmitting, the more the problems of design, right? The more expensive that transceiver becomes. And so as a result, if you want a cheap and cheerful, you just, we'll just send it as 4 times something, 4 times a rate that we know we can do cheaply. If once you get beyond that, you start having to look and say, okay, then, so we now have to, instead of paying, I don't know what the current price of a transceivers are, but for multimode, it was like $300 or $400 for a 100 gig optic, and $4,000, $6,000 for single mode. right? It's that kind of magnitude difference. So the cost of the fiber is kind of trivial, but the cost of the electronics that you need is significant. Okay. So yeah, I mean, that's about the excitement, really. Now you know everything there is to know. Obviously, the simple way to reduce choices is just to close down the size of this core. Yeah, if you reduce this in half, right? If our walls are down here, then obviously there's less ways for that light to come in, right? Less of it's going to get in to start with. You know, the outside ones aren't even going to hit it. And the ones in the middle, they've got fewer paths that they can actually take. And so what happens is this gets squeezed down until there's nothing left, basically. So this is kind of an example, right? This is that they are actually, you know, completely relative to each other to give you that feel of what we're working with, right? So with the old multimode, you've got this great big green thing. So again, the blue bit is the cladding. So they all have the same kind of diameter as a fiber. But the thing that we're interested in, the bit in the middle, is where we actually send the signal. Okay, so with the old ones, which are typically plastic, you had this kind of big space, and as a result, you couldn't really go very far, right? It was very limited in what it could do. But again, the speeds we were talking about in the bad old days were 10 meg, 100 meg. Yeah, it wasn't that we were going wild with distances. And obviously, the slower that you're sending the signal, the more tolerant your system's going to be, right? Because you've got more time for that light to pass along before you're making a decision. Is that a 1 or is it a 0? If we're only transmitting at 10 megabits instead of 10,000 megabits, then it's obviously a lot easier to make that distinction. Okay, so that's the logic. The newer optics at this point become just slightly smaller. It's now glass. They do some special things in this glass called grading, which makes the actual middle of it run slower. Yeah, it allows the traffic that's bouncing around the outsides to go faster. The further to the outside they are, the faster they'll go versus the middle. And so as a result, they all kind of join up in the, at various points along the fiber.
That's interesting. Okay.
So I'll admit I didn't know that. It's only as I was kind of reading that for this, trying to make some idea. There's a picture of it in the next slide anyway to show what it looks like. But trying to get that idea in my head was a bit weird to understand that. But it's just how they've treated that glass. They've put chemicals in there that cause it to be able to do this, right? It's all physics, and who cares? Yeah, that's for the physicists. We're engineers. We don't worry about how stuff works.
So this isn't organic fiber. This has been treated.
It's all been treated. Okay. Yeah, absolutely. Doped, I think, is the technical term. So they've been drugged.
Yeah, there we go.
Ian, can we talk about we've talked a lot about how fiber works and how data is transmitted and things like that, and some of the inner workings of the math even. But can we talk about myths about fiber that a lot of network engineers probably believe that maybe we need to clear up? For example, I I have heard, I don't know for sure if this is a myth, right? But I've heard from several different network engineers over my time that it's dangerous and can blind you if you look into an active fiber link on the other end, right?
And that's true. Ish. True-ish. Yeah. Everything has a grain of truth to it, right? That's the reality, because it's all based on something. So yeah, a laser can blind you. Okay. Absolutely, no question whatsoever. However, the power levels that we're talking about for normal transmission, not really that much of a threat unless you're sticking it in your eye. Yeah, after about 30 centimeters or so, the light's been dispersed so much that it's not going to have any impact on you, right? So if you put your head right up against a light source, it's no different than looking at a light bulb, right? If for some reason you feel the fascination of sticking your head inside the lampshade, turning the light on, your eyes aren't going to appreciate it, right? And it's the same here. Now, obviously, like I said, with the multimode, because the light's already, pretty spread out, it is just outside that visible light source, just on the visible light source, you can see it, right? So there is an indication. You can't, once it's passed through a fiber maybe, or not as clearly, because obviously, you've got the attenuation things of the fiber, but the reality is that it's not going to cause you any problem. It's not a James Bond movie where it's going to slice you in half.
So you're saying if we put our head right up to the port, we might get blinded. But if we put our eye right up,
what's going to happen?
Meters long, no, is that right?
The power, the optical power actually generates heat.
Okay, sure.
Right. So, and it's the same with the actual couplers, right? If you got two optical fibers connected back to back, you're going to get heat generated in that little tiny space between the two ends. Right? Not a lot of heat. It's not going to matter normally, right? But as the power increases, that becomes a problem, right? We can actually melt the fibers just because, the ends of the fiber, just because of the amount of power that we're pumping into there, right? And again, taking it back to sound, if someone's screaming into your eardrum, you're gonna not appreciate it, right? If they're doing it for long enough, it's going to damage your hearing. And it's the same with this. If you put enough light into your eye, you're going to pop the back of your eye. There's no question. But if you're doing that, then you've got other problems, in fairness.
Okay, that is fair.
So yeah, you should always be cautious, right? Because we don't want to take those chances. There's no reason to. But once you've got some distance between you and the end of the fiber, it's not going to matter, right? All of the inspection equipment that's used to check the end of the fiber, if you use any, it's either digital, so it's a video feed, so there's no way that you've got any chance of light getting through there, or it's already so it bounces around inside the scope around a whole bunch of mirrors, and so the distance between the end of the fiber and your eye is already way beyond what it needs to be able to be safe. That's again the reality. So yeah, I would never particularly worry about something like that. Something I did want to, just before we jump on from this, because these pictures don't do it justice, right? That because this is awfully big when you consider these numbers at the bottom, right? That the 62.5 is talking about the diameter of the core, right? 50 and 9, right? The 125 is micrometers. It's the diameter of the cladding, right? So obviously this is way, way, way scaled up, okay? The smallest that the human eye can see is 40 microns. So this is a quarter of what you can actually see. We're looking at a picture
of three different
4 times less than we're actually able to see.
Fiber cables, right?
Yeah, so this is a cross-section of the fiber.
So we have like two larger ones, right? And then we've got one with a teeny tiny little core in the middle. And that one's single mode, right? So
the first two are both the multimode, right? 62.5 and 50 micrometers. Yeah, I don't know what I'm talking about anymore. And then 9 down at the bottom here, right? They're thousandths of a millimeter.
Okay, so very small,
right? So
even the bigger ones.
The copier paper, the standard thickness of copier paper is about 100 microns. So the actual width of the cable of any of these, the cladding and the core, is just slightly. It's kind of letterheaded paper, right? That the thickness of a sheet of letterhead is the thickness that we're talking about for the full thing. Okay, if we were to magnify that fiber for single mode to the same size of a grape, then the core of the multimode would be about the same size as a grapefruit, right? Of a bagel, if you want, to some other food groups. if we push, if we magnify more and take that single mode up to about the size of a 1 cent coin, that 1 cent coin with the same magnification would be 12 stories high. Yeah, it's the Statue of Liberty, right? It's the actual statue. That's 12 stories. That's the size that we're talking about, right? We've magnified this to be 1 cent in size, and that 1 cent is now 12 stories. It kind of puts things into context. So that kind of comes to another thing that is a concern, that it's dangerous to work with fiber because it's glass. And the reason for that is because a red blood cell is about the same size as that core fiber.
Wow, of the single
mode. So if you're
mode?
actually working
A red blood cell.
Yeah,
Wow.
of the single mode. So if you're actually working with the fiber, if you're, cutting into them, you can't see that piece of glass. It's too small for you to actually be able to see, but it's plenty big enough to get into your bloodstream, right? It's going to pass through your finger pretty much without problem. So a splinter here is now a piece of glass that's running around your internal body. And, obviously blood has a tendency to circulate around the heart and the brain and all the rest of it. So there is a risk, but it's a risk for someone that's doing something with the fiber, right? They're working with the fiber. They've broken it open. Yeah, normal working with the fiber, it's not going to hurt you. It can't. There's no way
like a data center technician plugging things in, bundling fire, they're not really in any danger from something like that. You have one.
Can't see that. That's an absolute waste of time. So small. So when you're just wandering around plugging these things in, the end of the fiber, and obviously I probably can't get that in focus, but it's there. You can't see the fiber. In the middle of there's like a little, this thing here, which is where the fiber lives. But inside the middle of there's a little dimple. And inside the middle of that dimple is the core and the cladding.
Oh, wow.
Yeah, it's not something that you can actually see. So it's all good. So
we've talked about dangers of fiber. What other myths exist about fiber?
Okay.
Those were the two that I knew.
I got one.
Right
I got one.
That was how scary.
the other one.
It's glass. You better not bend it.
Glass, absolutely. It's a terrible thing, right? Because we know if you drop an actual glass or break a window, hit a window with a brick, it's going to break, right? So just as an example, somewhere here. Oh my God, it was here. I promise. There it is. So what I've got is just a kind of a little. Oops, I had. Where's everybody gone? I can't believe I hit that bang on the keyboard. The only way that could have gone better is if I disconnected. There we go. So, yeah, absolutely. That's more than enough Ian time. That's a phrase I hear quite often. So what I've got here is a visible light source, right? It's literally nothing more than a laser pointer. You can see the red indicator there. Nothing amazing, okay? So all we do, we plug this into a fiber. This is used for troubleshooting fiber because obviously normally you can't see light because it's outside of that visible space. But there you go. I mean, that's the excitement. That's the light passing down the fiber.
So you plug that into the one end of the fiber and then you hold it up and you can see the light come out the other end. And that is, what's that tool?
Yeah, and this will pass. This is a visible light source, a visual fault locator.
It's used for
VFL.
Locating faults in fiber by shooting like a visible light through it, so you can see if there's a fault in the fiber. Is that what that's for?
Yeah, it's no different than using like a toner on an electrical cable, right? You put something that's generating noise on one side or an electrical signal on one side, and you can pick it up on the other. You obviously can't see it because it's electrical. We have the advantage with optics that, hey, it's light, yay. So yeah, I mean, this is used mostly for troubleshooting fibers, obviously, but also for being able to find where it goes to, right? If you've got a patch panel with 1,000 cables in it, the last thing you want to do is to start tracing every single one. So you find the one end where you're interested in and look for the end that's glowing, right? That's the good indication as to where it comes out. So that's the excitement. But what it allows us to do is to actually demonstrate kind of what happens, because light travels in straight lines, as we were just talking about. And so if we put a loop in there, you can see there's not really all that much excitement happening. The light's still passing around. It's still quite happy. As we make this loop smaller, what you'll see is it starts to glow red. It is a little bit red. Can't really pick it up. Come on, at some point here, I promise. Yeah, so it is. I promise. You can start to see it there. And now, because it's adjusted color, we can see that there is a very red tinge to it. The more that gets pulled, the more light is escaping, because that's all that's happening, right? The light's bouncing along quite happily. The light we can see is the stuff that it can't get bounced back into the fiber. So this is all loss. Okay, this happens a lot inside data centers, right? Because it's just a cable, so it doesn't matter if we stick a bend in it, right? But it's glass, it breaks. But as you can see, it's gone, right? We popped it out. We didn't pull it far enough for it to break. So
you bent it quite a ways to
here's
really,
another
just
example.
to summarize for our podcast listeners, you bent this in a loop quite a ways down to be very small. And we did see the light escaping at the end, sort of at the top of that loop, but you straightened it back out just now and everything's normal. Nothing seems wrong.
Yeah.
Right.
So here's a fiber that is what you call broken. It's a very technical term. I'm sure your listeners are familiar with the term. And if we look at the end, there is no light passing through it, right? This is glass. So what we can do is, just to kind of prove the point, we can pick a point, and go through that same exercise again, right? So we're just going to stick a loop in here. We can keep pulling, and I wouldn't recommend doing this in production particularly. And it still bounces back.
So you can bend it quite a ways without it actually breaking.
You can bend it quite a way, but if you look, I don't know if you can actually see it there.
Oh, a little bit, yeah.
Somewhere. It doesn't take nearly as much to actually have light escaping. So we've damaged it. Yeah, so the attenuation of this cable is now higher than it was. But it would still pass light if it wasn't for that small break further down. If we go really crazy, and this happens a lot when people are pulling a cable, because it'll just get snagged on something. That's now, I didn't quite get it, but I've made it a lot worse, right? If I actually tread on it, we're pretty much done at that point. Yeah, there's no way I would trust that in production, because it's quite easy to get a 90-degree bend, and now we're losing a good chunk of light through that.
Interesting.
Okay. Obviously, we can't normally see this, right? We can only see this because of the visible light source. So that's why it becomes kind of a good practice to treat this nicely.
Do you know if are these tools, these visible light sources, common in data centers for technicians to use?
Yeah, they would normally be in a standard toolkit, because they're like $20-$30. Okay. They're not. It's an LED light, right? There's nothing amazing about them, and the amount of time it saves for patch panels, right? Not for playing like this, but if you are stood in front of your equipment and you say, okay, then port number 5, I can plug it in there, and you want to go find out where it comes out of the other end, you plug that in and you just go hunting for, where can I see the glow? Yeah, now it's nice and easy to find, and it's all good. So yeah, they're good. This will go, I don't know, 10 kilometers, something like that. So it's intended for kind of fiber to the home kind of applications, so that people working out in the street can do the same thing, right? Because again, we can't tell whether the fiber's good or not. To get more accurate visibility into the fiber, there is expensive test equipment we can buy, but for the sake of an LED and a battery, this works pretty well in a lot of cases. So, but yeah, it makes it visible. But one thing that you saw is it wasn't that fragile, right? We had to go out of our way to get it to the point where it actually became a problem.
So that's kind of our myth, right? Is that glass, I think a lot of people might have the impression because it's glass, you cannot bend it really at all or much. Right. But what you just showed us shows that you can bend it quite a bit. You probably don't want to do that, but if it does
you don't
bend,
want to do it, but if it happens,
probably, right?
And it's droppable. It's all good. It'll bounce, right? It's covered in plastic. It's not fragile. And the other thing is that inside that outer plastic sheathing, there's Kevlar strands. So you can't break it by stretching it, right? The Kevlar gives it that strength, so you can pull it quite easily, dragging it across the data center or whatever, as long as you're not doing stupid things like, tying it up into something so that you can drag it, and introducing a knot or something where you've just broken the very thing you're trying to run in. So they're not fragile, is basically the bottom line, but you want to be careful, right? The ends are really the fragile piece of all of this, which is why you want to keep dust caps on. Yeah, it's good from an optical safety point of view, because obviously if you've got a great big piece of plastic on the end, it doesn't matter how close you get your eyes to the port, it's not coming through that plastic. But more importantly, it's protecting that delicate little thing in the middle of all of this, which matters, right? A grain of dust is bigger than the core of the fiber. If you put a fingerprint on the end of a cable, it looks horrendous when you actually look at it through a microscope, right? The grease and the stuff from your fingerprint it has such an impact here that you want to be kind of careful with the ends and clean them and all the rest of it. But, if you're not getting them dirty to start with, then that's the best way.
Cool.
Don't drag them on the floor.
So you can be a little rough with it, but not too rough is what we're learning, right? It's not that dangerous, but be careful is what we're learning, right? Yeah.
It's not dangerous, right?
Just be careful.
Yes, it can blind you.
If you try hard.
But you've got to be stupid. Yes, you can get it into your bloodstream, but you've got to work at it,
Okay, that makes me feel better.
Yeah, for sure.
As someone who never works with fiber ever, it makes me feel better.
Yeah, you can probably hang yourself with it, right? It's Kevlar, so it's all nice and simple. If you're looking for ways to hurt, but no,
dear listeners,
I would not recommend any of these actions. Don't try this at home or at work.
Okay. Well, we're close to wrap up time, Iain, but is there anything else that maybe we didn't address that you think is interesting or something we should know about the basics of fiber optic networking?
Something you should know. Really, there's not that much, right? So I'm just going to very quickly fly through the rest of these because I know we're out of time and it's all good. I'm sorry, I just ramble on too much. And you end up with this nonsense.
We're getting something out of it.
Sure. I warned you, right? The reality, right, is when we come to what the connections are and how they work in a data center, there isn't a difference between single mode and multimode for how we work with them, right? It's the capabilities of what they're able to provide us, but the connectors are going to be different potentially. But as you can see here, the blue ones we've got, they're multimode. These yellow ones are single mode. They look exactly the same. They work exactly the same. They plug into the same transceivers. But you can't mix them up, right? You can't plug a multimode into a single mode because the difference in size, right? That mismatch there makes such a big difference. Are single mode
always yellow and multi-mode always blue colored cables?
No, that would be nice, wouldn't it? In the bad old days, yes, that was true. The multi-mode was always orange. The single mode was yellow and nice and simple. But then people started getting imaginative and saying, oh, you can have turquoise fibers for your voice and, fluorescent indigo for your data and, and things kind of got crazy. And then different types of optic as well. So Multimode has, ON2, ON3, ON4, ON5. Each of those different types of fiber have different colors, different properties. So there's nothing exciting about them. That's kind of the bottom line, that, when we're using them, it all looks the same, but we can't mix them up. This was just flying through, they're talking about the breakout cables that you mentioned there very quickly, Tim. This is an MPO, a multi-port optical cable. In this case, it's got, there's 12 fibers that run through it, and it lines up on each connector on each end. And this is what I'm talking about with density, right? You cannot possibly get an Ethernet cable that is this small to carry. In this case, we've got 4 pairs, 8 fibers inside that one cable. So the equivalent of 4 Ethernet cables, just in something that's the same size as a normal optical cable. Yeah, that it can't be done. There physically isn't enough space. So these were also much more. That was just kind of a very quick how it works with single mode and stuff, but we can live without that. It was all good.
I have a couple questions. So we've used both of the words that I'm going to bring up here in a second in this show, and I've also heard them outside of this show as well. And I'm trying to figure out if they're different things or if they're interchangeable. So when we're talking about the actual piece of equipment that sends and receives the light, I've heard optics and I've heard transceivers. Are those interchangeable, or are they different things?
Good question.
There's a whole bunch of words, right? You've got SFP, XFPs, which are talking about the specific type, right? All a transceiver is it's making a change, right? It's taking an input and putting it out as something else. Right, it's translating the input. Right, it's translating what it's receiving into something else. Transceiver. Okay, so yeah. I mean, maybe that's me being a bad person, because it would normally be used as a piece of equipment. It would be a card that's converting from those wavelengths that we use, so the 850 or the 1310 that we use inside the data center, to a very, very specific color of light that we use, to leave the data center in something like a transmission system, right? Where instead of, one color of light on that fiber, we're putting, hundreds, but 120, 60, whatever the magic number is at the moment. So because each color, going back to that prism again, can pass into that white light and be treated independently, as long as you've got the ability. So, sorry, I know that we're done, but sure, there's already a picture for it, so there's no point in trying to pretend. Otherwise, slideshow, we're not doing it from the beginning, from current. So this is the idea, right? That this is a single mode, but this helps to build things out. With the multi-mode, like I said, you had 4 independent lasers, wherever it is. I don't have it, but it's fine. You got 4 independent lasers providing a transmit and receive on the 4 independent pairs of fiber that you've got inside this connector. So it's all straightforward. They're all just 10 gigs. When we get to single mode, because we can only have a single fiber, because we're going distance, right? You can't have 4 pairs of fibers. It doesn't make commercial sense at that point to have 4 separate pairs over 2 kilometers, right? It makes a lot more sense to buy a more expensive optic and use a single fiber pair. Okay, so literally what happens there is we get 4 different colors generated by the transceiver, blue, by the optic, by the optic, by the SFP, So it's injecting those 4 different colors in the same way. We multiplex it, we demultiplex it on the receiver and break it back into those individual colors. And when we look at the fiber, if we actually measure on there with a special light frequency sensitive measurement, its name's failed me. I'm sorry, it's a bit late now, but yeah, when we're looking at there, what we're going to see is those 4 separate colors, right? It's able to measure light at all those frequencies, even though it's all one fiber. Yeah, and so the transceiver is basically to take a color in, so a 1310, for example, and convert it into something else, into 1552.7 or whatever it might be. An optic is an optic. It's an optical interface. But like I said, we've got SFPs, which are small form pluggable, XFPs, which is a 10 gig version. There's SFP pluses, which are for the they're all just terms. It just depends on what vendor, what time, what interface it looks like. Sorry, not a long answer, but not a good one.
It's very interesting, I gotta say.
Iain, what sort of magnetic material is on fiber optic cables that attracts large construction equipment with sharp blades?
Now that is a very scientific question. It's called Murphy's Law, obviously. I mean, that's it's a huge problem, right? It's in a data center, fiber's safe. It doesn't have any natural predators apart from clumsy technicians.
Are you sure? I've heard of sharks chewing on cables in the sea.
Sharks typically don't do that inside a data center, though.
Fair.
And and it's very specific cables. Normally they're underwater, Lexi. I mean, I think that should be a clue. And I apologize. That was uncalled for on my part to draw attention. But yeah, Google had a suite of problems with sharks.
Yeah.
But no, I mean, fishing is a problem for undersea cables, right? Because they're dragging an anchor, they're suddenly coming across something on the seabed, a cable that stretches across, and surprisingly, a motorized fishing boat with a big sharp anchor, it does battle against these cables. They're well armored, they're well protected. Same with the construction equipment, as you were saying, Tim. Because they're in so many places, typically running along the side of a road, or it's quite common that someone is gonna run into them. They're also wrapped around the overhead power cables in a lot of cases. That's another way they get from one place to another. It's a lot easier than digging a street up to bury them. You string them up on the overhead power lines, but they're susceptible to to things like wind, right? Because they're moving, you've got that same problem that you have when somebody's bending it, or the characteristics of the fiber change. So you get all sorts of new problems then, and anyone running into those power cable, into that power line, cars have an awful tendency to run into power posts.
Unfortunate and
anyway,
tragic.
What the actual answer is? Yeah, it's Sod's Law, Murphy's Law. If it's going to happen, it'll happen. There's no two ways about it.
Well, thank you so much for educating us today, Iain. This was really awesome.
I love that caveat.
If you want to be found, where can people find you? And I know that sounded incredibly creepy, but where can people find you?
I'm always hiding under my desk.
Other than at your desk.
Fearing the day that someone will notice.
Do you want to share your Twitter? Do you have a Twitter?
I've been influencer.
Yeah, so it's just at Network Doozer or something. That shows you how much I care, right? I'm an influencer, obviously. It goes without saying.
But you're active on Twitter. Okay, so Network Doozer on Twitter. Anywhere else you want us to find you at on the internet?
Not really. I'm not particularly well socially connected, I guess is the technical term. I'm an old guy. No one needs to talk to me.
We just spent an hour and a half talking to you, so obviously. No, thank you.
But you're
That's
biased,
true.
in fairness.
That's true. You're one of my favorite people. Thank you so much for being on the show, Iain. Thank you for educating us. Optics are so interesting.
You're welcome.
Yeah,
Thank you for the invite. Hopefully it was of use.
Is there any way we could maybe get a copy of the slideshow that you had for us today and
yeah, of
maybe
course.
post on the website or something for people to take a look at, before, after, during their, if they want to listen to the podcast?
Yeah, again,
this will also be a YouTube video, but
it's not amazing, but hey, it was just reinforcement.
It has some very helpful visuals.
So yeah,
you.
I'll send that on to you.
Awesome. Well, thank you also to my awesome co-host, Tim Bertino. Thank you for joining us as well, Tim. And thank you to our awesome Patreons that joined us live today for our episode recording. If you want to be really cool like them and hang out with us before, during, and after our live episode recordings, you can visit patreon.com/artofneteng and sign up to be a Patreon. As a special perk of being one of our Patreons, you also get access to our Super Happy Fun Times channel in our Discord. It's all about the journey, as well as updates about our schedule and future episodes before everyone else gets them. So thank you all for joining us, and we'll see you next time on The Art of Network Engineering. Hey y'all, this is Lexi. If you vibe with what you heard us talking about today, we'd love for you to subscribe to our podcast in your favorite podcatcher. Also, go ahead and hit that bell icon to make sure you're notified of all our future episodes right when they come out. If you want to hear what we're talking about when we're not on the podcast, you can totally follow us on Twitter and Instagram at Art of NetEng. That's Art of NETENG. You can also find a bunch more info about us and the podcast at artofnetworkengineering.com. Thanks for listening.